Hey there. So today I'm going to talk about something that I think is actually really cool. Diffie-Hellman Key Exchange. I know you're probably yawning already, but you know what? Stick with me because it's fascinating. It's very interesting, very cool. Hopefully it'll be something that you have an appreciation for when I'm done. So, Diffie-Hellman Key Exchange. Back in the 70s, these two guys, Whitfield Diffie and Martin Hellman. They were two, I don't know, math geeks, I guess you could say. They were two guys. They came up with this idea of being able to generate a shared secret between two parties in such a way that the secret can't be known by observing the communication, right? So think about that for a second. Two people talking, they can exchange a secret, or actually it's generate a secret, build a secret, and you can be sitting there watching them, listening to them the whole time and not get what the secret is. I think that's pretty cool. Anyways, it's done through some very complicated math, but that's how it works. And we use it all the time now on the internet. TLS uses it, SSH uses it. We just take it for granted because it just happens, but it's very cool. Now, it's pretty easy to explain, but like I said, it is complicated math. So rather than using math to explain it, I'm going to use colors. And if you ever take a security course and they try to explain this, there's kind of this universal chart, which is actually even on Wikipedia. Maybe I'll try to put that in here as well, into the notes for sure anyways, that explains it. But I'm going to give it to you in a pretty simple way, where you'll just get to understand it. But remember, the color is just an analogy, right? It's not really about colors. So, all right, you and I, we need to establish some cryptographic communication with each other, but we are on an untrusted network. We are on the internet. People could be watching what we're doing. They could be listening to our traffic. Our traffic could be being recorded somewhere. So how do we build a secret that you and I both know to use for our encryption? Well, Diffie-Hellman Key Exchange. So it always starts with a common color, right? It's not really a color. It's a prime number and a generator number, but remember, this is an analogy, so color. So we start with a common color, and in every example you ever see, it's always yellow. But I mean, it's a random color. It could be anything, but for the sake of the demonstration, we'll stick with yellow. So, all right, we're starting with yellow, the yellow color. Now, to the yellow color, you add some random color that you think of, and I'll add some random color that I think of to my yellow. And what'll happen is I'll get a blob of color, and you'll get a blob of color. That blob of color, through the math that we did, is basically the public key. So we can exchange that in clear text. I send you my color blob, you send me your color blob. Somebody who's watching, they're going to know that we started with yellow, and they're going to see these color blobs go by, but that's all that they know. Now, I take your color blob and I do some magical math involving the color that I previously picked, and I arrive at a shared secret. You take my color blob and you use the color that you previously picked, and you do the math magic, and you arrive at the same shared secret. That's basically the private key. So now we've just exchanged public and private keys, basically, in full view of somebody else, and they have no idea what it is. Again, very simple to explain, but there's complicated math involved there. I know you can kind of envision in your mind a way of how you make the two sides of the equation equal. It's not quite like that, and if you look at the math on the Wikipedia page, you'll kind of see that. But basically, what happens is we now have exchanged keys that are basically intractable to reverse. Not 100% impossible to reverse. I imagine if you had enough time and money and worked for a certain three-letter government agency, it could probably be undone, maybe. But for all intents and purposes, it's very computationally expensive. That's the wording they like to use, and it's basically intractable. So it's secure for you. Now, on top of that, we can do this process, but we can do it ephemerally. And when I say it's ephemeral, I mean it's temporary. So on the fly, we just pick that random color, we do the exchange, and we have our communication session with that key. Then when we're done, that key gets thrown away. Doesn't get recorded anywhere, doesn't get saved. My communication, your communication, it just happens, and then those keys are gone. Now, if another session has to occur, we'll do that again, right? We'll do different colors and we'll do a different exchange. This is what forms the basis of perfect forward secrecy, right? We've got new unique keys happening every time. That means if by some weird fluke chance somebody happens to break one session, the rest of them are still safe. They've got different keys, they're still secure. So yeah, this is how Diffie-Hellman Key Exchange works, and it's really cool. I think it's very neat. I hope that when you kind of break this down and look at it, that you can appreciate what's going on there too. It's just a cool thing, and I remember when I first learned this, I thought, is that ever neat? Hopefully it's neat for you too. Alrighty, that's all I got for you today. Have yourself a great weekend.